Hi, this is Mrs. LaBarbara. This is AP Physics, Universal Gravitation, review number 4. Two stars, A and B, are in circular orbits of radii RA and RB respectively, about their common center of mass at point P as shown above. Each star has the same period of revolution t. Determine expressions for the following three quantities in terms of RA, RB, t, and fundamental constants. A. The centripetal acceleration of star A. Centripetal acceleration equals to v squared over r. What is v? V is the speed. Speed is distance over time. In a circular motion, that distance is 2 pi r. Over time is the period. So v equals to 2 pi r over t. We substitute this expression into the equation for centripetal acceleration. We have a centripetal acceleration is 2 pi r over t, the whole thing squared divided by r. Simplify this, we have centripetal acceleration equals to 4 pi squared r divided by t squared. Now for star A, the r for star A is just RA, so AC equals to 4 pi squared RA over t squared. Next one, determine the mass MB of star B. To determine the mass, we have to consider the equations has mass. So in this case, what do we use? What equations can we use to have mass? We go back to, to the force. Net force equals centripetal acceleration. So net force is centripetal force. In this case, the net force is gravity. So gravity, Fg equals to Fc. Gravity is Gm. M1, M2 over R squared. M1 is MA, M2 is MB. R is the distance between the two stars, which is RA plus RB. That equals MAC. We'll already know from last question what AC equals to. So we set two equals to each other. From there, we can solve for MB. As you can see, you don't have to worry about MA in this equation because MA cancels out on both sides. So substitute AC in, you will have MB equals 4 pi squared RA times RA plus RB whole thing squared divided by t squared times G. Similarly, the mass of MA of star A, we use the same logic. Gravity provides centripetal force and set the equation. Let's see if we can find what MA equals to. So if you are having trouble, you can take a look how I did it. So again, for star B, the equations are the same, have the same logic, except in this case, AC equals 4 pi squared RB divided by t squared. This is the centripetal acceleration for star B. Then substitute this into the equation. We have MA equals 4 pi squared RB times RA plus RB squared divided by t squared times G. So for the mass of A, we have to use distance RB, and for mass of B, we have to use distance RA. Next question, determine expressions for the following two quantities in terms of MA, MB, RA, RB, and T, and fundamental constants. D. The moment of inertia of the two-star system about its center of mass. So according to the definition, moment of inertia for a particle, system particles is the sum of mi ri squared. So for this system, there are two particles, stars A and B. So we simply add them together, ma-ra squared plus mb-rb squared. Last question, the angular momentum of the system about center of mass. Let's see, since two stars are rotating with the same revolution and the distance between those two is constant, what that means is the two stars must rotate in the same direction. That means they are either both rotating clockwise or both rotating counterclockwise. That means the momentum is simply add them together. Since we already know the moment of inertia of the two-star system, and we simply multiply the angular velocity. The angular velocity has to be the same. How do we know that? Because they have the same period. That means, remember, omega is the degrees, so same period, that means they each going one round in the same time, so their angular velocity has to be the same. So L equals I omega. We already know what I is. We know omega is. Omega is the angle over time. So for 1 revolution, the angle is 2 pi. From there, we can figure out L. Simply substitute I and omega in. You'll have L. Whoops. You'll have L equals to I times omega. That's it. I hope it helps and see you next time.